A very good morning to one and all. I welcome you all for the session number 34. In this session, we will have a small qualitative discussion on Hamiltonian formulation. We have seen how Newton's laws of equations of motion can be obtained from Lagrangian formulations. So in the last session, we have discussed on the applications of Lagrangian equation for a linear harmonic oscillator, where its kinetic energy and potential energies are obtained and substituted in the equation L is equal to T minus V, which is half mx dot square minus half kx square. And solving Lagrangian equation, we arrived the equation for linear harmonic oscillator to be x double dot plus omega square x is equal to 0. And the general solution for this is x is equal to a cos omega t. So this is what we have studied in last class. The main objective of this session is to understand Hamiltonian formulation, which is a qualitative discussion. In your higher studies, you will learn much more about Hamiltonian formulation. The outcome of this present session is to understand how Lagrangian mechanics is superior over Newtonian approach and Hamilton formulation. We know that Newton's laws of motion, it is second law, where force, momentum, acceleration, they are all vector quantities and they need vector algebra to solve problems. However, if we don't know all the forces acting on a body, then arriving to the solution for a given problem will be very difficult. Even though we commonly use some coordinates, to obtain the solution to the problem will be impossible in Newtonian approach. These drawbacks of Newtonian approach is overcome by Lagrangian mechanics by using generalized coordinates which are compatible with constraints. And we have seen how generalized coordinates are used to obtain generalized velocity, generalized force, generalized displacement, generalized momentum. All these are scalars and they need normal algebra treatment. Further, note that Lagrangian form of equations are invariant under any generalized coordinate systems. In the couple of sessions we have seen, we have utilized plane polar coordinate system, Cartesian coordinate systems, and the Lagrangian, when we found that Lagrangian equations are invariant under any generalized coordinate transformation. This is the beauty. Now, we have seen the Lagrangian, which is a function of q dot t, and L is equal to t minus v, and Lagrangian equation is d by dt of dou L by dou q dot minus dou L by dou q is equal to 0 for conservative forces. On solving these equations, we have obtained a second order differential equations. So in Lagrangian mechanics, a second order differential equations are obtained. However, an alternative formulation is given by Hamilton, making use of generalized momentum in place of generalized velocity. In Hamilton formulation, two sets of first order differential equations are used instead of a set of second order differential equations. Solving a first order differential equations will be very easy compared to a second order differential equations. But however, note that both Lagrangian and Hamilton formulations, they both are equivalent. But the Hamilton formulation is more fundamental because it gives a foundation to statistical and quantum mechanics. We have seen the Lagrangian mechanics is a function of Lagrangian is a function of q dot t, and L is given by T minus V. T is kinetic energy and V is potential energy. The Lagrangian equation is given by d by dt of dou L by dou q dot minus dou L by dou q is equal to 0. However, in Hamiltonian mechanics, a generalized velocity is replaced by generalized momentum, which is given by h as a function of q, p, t, and h is given by t plus v. Here t is a kinetic energy and v is the potential energy. Here we see that we obtain a second order differential equations. Here we use two sets of first order differential equations, that is dou h by dou q r is equal to minus p r dot, and dou h by dou p r is equal to minus q r dot, and dou h by dou t is equal to minus dou L by dou t. However, if Hamilton is independent of time, then this term is set to 0. Then we have two set of first order differential equation, is dou h by dou q r is equal to minus p r dot, and dou h by dou p r is equal to minus q r dot. So we see that a set of second order differential equations will be replaced by first order differential equations in Hamilton mechanics. So Hamilton mechanics or Lagrangian mechanics will be far better when compared to Lagrangian mechanics. However, note that both the formulations are same. So in this session, we have learnt how Lagrangian mechanics uses generalized coordinates to overcome Newtonian mechanics drawbacks, and the Lagrangian form of equations are invariant under any generalized coordinate transformation. In Hamilton equation, the generalized velocities are replaced by momentum. You see that in Hamilton mechanics, two sets of first order differential equations are used instead of a second order differential equations. So in this classical mechanics, we have seen a reformulation of Newtonian equation of motion by Lagrangian as well as Hamilton. However, Newtonian mechanics are reformulated by Lagrangian and Hamilton. In Lagrangian mechanics, we have second order differential equations to be solved, whereas in Hamilton mechanics, we have first order differential equations. So we see that Hamiltonian mechanics, Lagrangian mechanics and Newtonian mechanics deals with the same equation of motion of our body. However, Hamiltonian mechanics are very far better because they will give a foundation for to understand statistical and quantum mechanics. So now let's have a small session on MCQs. In Newtonian mechanics, physical quantities used are only vectors. Question number 2. Solving equation of motion using Newtonian mechanics is difficult because all the forces are not known and constraints involved are not known. Question number 3. Lagrangian equations of motion are invariant under generalized coordinates. Lagrangian is a function of, we are saying L is equal to Q dot T. So option A. Question number 5. Hamilton is a function of QPT. So option is B. Question number 6. Hamilton term is given by H is equal to T plus V. So option is A. Question number 7. In Hamilton formulation, how many set of first order differential equations are used? You know, we use 2 set of first order differential equations. So option is B. Question number 8. Hamilton formulation is more fundamental to the foundation of dash and dash mechanics. Option is both statistical and classical mechanics. So option is C. Dou H by dou QR is equal to, option is minus PR dot. So option is C. Question number 10. Dou H by dou PR is equal to minus QR dot. So in this session we learned how Hamilton formulations, we have discussed Hamilton formulation qualitatively. Hope you have enjoyed this session. Thank you all.